You know, when you think about heat-seeking missiles, it's all in the name, right? They're built to find the hottest thing around, like a jet engine. But hang on, there's a much bigger, hotter thing in the sky, the sun. So why don't they just make a beeline for that? Well, that's a fantastic question, and we're going to get into it.
I mean, really think about it. How on earth do you design a weapon that's supposed to find a tiny little campfire when it's sitting right next to a star? This is the problem missile engineers have wrestled with for decades. And the answer, as you'll see, isn't just one simple trick. It's actually a whole series of incredibly clever solutions layered on top of each other. And believe me, getting this right is a matter of life and death. Just to put it in perspective, between 1984 and 2009, infrared missiles like these accounted for a jaw-dropping 90% of all U.S. air combat losses. These things are devastatingly effective, which is exactly why teaching them to be smart enough to ignore the biggest distraction of all is so absolutely critical. So, let's start by just framing the challenge here. We're talking about what you could pretty accurately call the billion-degree problem. The scale is just immense. Just look at these numbers. The sun's surface is blazing away at 6,000 Kelvin. Now, a jet on full afterburner, one of the hottest things we can make, tops out at around 2,000 Kelvin. So the missile has to spot that relatively dim heat source while a stellar bonfire is raging right next to it. So how in the world do they pull this off? Well, the very first line of defense is all about being selective. The missile isn't looking for all heat, it's looking for a very specific color of heat. You see, the sun pumps out energy across a massive spectrum of wavelengths. But a jet engine, its heat signature shines brightest in a very particular slice of that spectrum, the mid-wave infrared band, right between 3 and 5 micrometers. So engineers basically put a special pair of sunglasses on the missile sensor, a filter that tunes it to see only in that narrow window. It blocks out almost everything else, making the jet's specific glow pop. And this is where it gets really, really brilliant. There is a magic spot at exactly 4.3 micrometers. At that specific wavelength, all the cold CO2 that's just floating around in our atmosphere acts like a curtain, absorbing and blocking the sun's heat. But the super hot CO2 being blasted out of a jet engine shines like a searchlight at that exact same wavelength. The atmosphere itself creates this private, invisible channel where the sun goes dark and the jet engine is the only thing that's lit up. It's an absolutely genius trick. Okay, so filtering is a huge help. But what if the sun is still kind of in the frame? Well, the next test doesn't care how bright the target is. It cares about how that heat signal behaves over time. Think about it this way. The sun is a giant faraway ball of gas. Its heat signal is incredibly stable and constant, just a steady, unwavering stream of energy. A jet engine, though, has all these spinning turbine blades inside. As they rotate, they constantly chop up the heat signature, making it flicker, or pulse, really, really fast. The missile isn't just looking for a bright light. It's looking for that specific flicker. And this all comes down to the electronics. The missile's brain is basically programmed to hear two kinds of music. It's told to completely ignore a steady, flat DC signal, that's the sun, but the instant it detects a high-frequency pulsing AC signal, the telltale rhythm of a jet engine, it's designed to lock on and amplify it. It's listening for a very specific beat. Now, those first two tests were game changers, but then technology took a massive leap forward. Missiles went from just seeing a point of light to seeing an entire picture. The original seekers were pretty simple. They just saw a single pixel of heat, basically a hot dot in the sky. But modern imaging infrared seekers, or IIR, use a grid of thousands of sensors. It's the difference between a single light meter and a full-blown thermal camera. Now the missile can see a complete thermal image of what it's looking at. And once you can see an image, you can use software to recognize shapes. To the missile's computer, the sun is just a simple, round, fuzzy blob. An aircraft, on the other hand, has a very distinct and complex silhouette. Wings, a fuselage, a tail. The software is programmed to look at that simple circle and just say, nope, not interested, while it hunts for that complex aircraft shape. So in just milliseconds, its onboard computer is running through a quick checklist. It's asking itself, is this shape complex or just a simple blob? Can I actually make out the edges of a plane? And crucially, it starts tracking the target's center of mass, the middle of the whole aircraft, not just the single hottest point. That's what keeps it from getting tricked by a flare or the bright center of the sun. And that brings us to the fourth and, you could argue, the most elegant test of them all. This one is just pure physics and logic. The missile judges a target based entirely on how it moves. Here's the logic.
Because the sun is so incredibly far away, its position in the sky is, for all practical purposes, fixed. Any movement the missile sees from the sun is actually just a reflection of its own turns and maneuvers. A real aircraft, though, is much closer and moves independently. It has its own flight path.
This whole process has a great name: kinematic discrimination. The missile's computer constantly calculates the movement of the heat source it's tracking, and if that source stays perfectly still relative to the missile's own body, if it has zero independent movement, the logic gate makes a simple conclusion: that thing must be infinitely far away. It rejects the target because its behavior is physically impossible for any aircraft. So, you put it all together: the filtering, the flicker detection, the shape recognition, and the movement logic, and you have the layers of protection that make a modern heat seeker work. But this tech didn't just appear out of nowhere. It's the result of a long, high-stakes, and frankly, unending arms race. You can see this whole story play out in the evolution of one famous missile, the Sidewinder. The early versions back in the 50s were, well, pretty basic. They got fooled by the sun all the time. But by the 70s, they had incorporated much better filtering and that flicker rejection we talked about. And today's version, the AIM-9 ARCS, uses a cutting-edge imaging sensor with all 4 layers of logic baked in, making it almost completely immune to solar interference.
But of course, the second missiles got this smart, the other side had to adapt. Modern fighter jets are now equipped with countermeasure systems that don't just distract the missile, they actively fight back. They use a high-powered laser to actually find the incoming missile's sensor and blast it with a modulated beam, essentially trying to blind it by creating a new artificial sun that the missile just can't ignore. And that brings us right back to where we started. This is a relentless cat-and-mouse game of physics, software, and light. As the missile seekers get smarter, the countermeasures get more powerful, and the cycle just continues. It really makes you wonder, in this unending technological race, can a missile's electronic brain ever be made truly 100% foolproof?